So today we are going to discuss a new advanced surface characterization technique. The name of the technique is Auger electron spectroscopy, or in short it is known as AES. We have discussed about the SPS or X-ray photoelectron spectroscopy in details. So some of the concepts I will borrow from the XPS to the AES, but I will have to discuss many other new things in the advanced spectroscopic technique. So therefore, I need to constrain myself so that time does not go out of order. So in Auger spectroscopy, basically the materials which I am going to use here are taken from different sources, but most notably this book is the source of the material for all the spectroscopic techniques in the Encyclopedia of Materials Characterization, edited by Bundle, Evans, Wilson, published by Butterworth, Hinman, Boston in 1992. The schematic representation or the outline of the particular lecture series on AES is as follows. First, I will talk about some historical perspectives of Auger electron spectroscopy, how it has come about it. Then I need to discuss in detail about the basic principles, and you must know very well that. Then there are certain nomenclatures which are used in AES like any other techniques. Then I will go to AES spectra, how any spectra of AES, how does it look like, what are the information we can obtain from there. This will be followed by discussion on the other effects. There are many other effects, and obviously some amount of instrumentations we need to discuss, and in all this many examples will be given to show you how relevant this technique is for different applications in material science. So let me just start with the historical perspectives. As you know, Auger electron spectroscopy is a very widely used technique for surface characterization of materials. It is used to know the electronic states of different elements present in the surface. It can be used to measure compositions of the different elements on the surface. This is a non-radiative de-acceleration process, unlike XPS where you are using an X-ray source to eject out a core level electron from an atom, and that's how, and then the electrons comes out from the material and measure the kinetic energy of the core level electron and do remaining other things. This is not like that. This is a non-irradiative de-excitation process. Remember, this is not excitation, but this is a de-excitation process, but this is also non-irradiative. That means we are not irradiating, we are not getting this phenomena because of irradiation like in XPS. This de-excitation occurs obviously by Coulomb interaction, where an atom loses energy by emission of one or more electrons, and then the ejected electron to one continuum state is what is known as Auger. Obviously, at the beginning definition will not be clear to you. It needs to be discussed, it needs to be talked about it. I am going to do that in the basic principle stuff. But first is was discovered in 1923 by a lady named Louise Meitner, or Lee Meitner. Basically, her picture is shown here. These are all taken from different books. And after 2 years, in 1925, this was independently discovered. It seems this was independently discovered by Pierre Auger, and after his name this spectroscopy is coined. This is Pierre Victor Auger picture, you can see there. This paper by Auger was published in Journal of Physics Radium in 1925, and this process is named after him. To give you even how the developments took place later on, let me just talk in little detail. So therefore, in 1923-25, the effect was discovered independently by Meitner and Auger. Meitner published his paper in Journal of giant script for physics, and Augier published in Journal of Radium. Their pictures are shown here, but then there was a brief lull, nothing happened because of, obviously because of instrumentation problem. 1953, Jens Lander uses electrons to create excited Auger electrons, and those Auger electrons are used to study the surface impurities. The problem is basically the vacuum system, because these electrons which are created by the Auger process are very low energy, so therefore vacuum has to be very good to detect them, and also obviously detection system needs to be developed. Then 1968, so that was 1953 by Lander, and 1968 L. Harris demonstrates the usefulness of this technique when he differentiates the energy distribution of Auger electrons emitted from a bombarded surface. At the same time, Weber and Perria employed lead optics as Auger spectrometers. Lead I have taught actually low energy electron diffraction. This will be taught by my fellow colleague. So, lead actually is what's called lead optics can be used for Auger for detection system. That was done by Weber and Perria. Then 1969, Plumbers et al. Invent the cylindrical mirror analyzer, or is known as CMA, which greatly improved the speed and sensitivity of the technique. So, you can see from 1925 to 1970, almost like 35 years took to develop this technique to be useful, and then in mid 80s saw the real implementation of this technique because of the Schottky field emitters as electron source. Schottky field emitters has a very high brightness, this we discussed in the electron microscopy. So, this allows actually to analyze, remember surface features size of 20 nanometers, very small size. And then in fact afterwards 1990s, even beginning of 1990s, a lot of improvement happened in analyzers actually and sources. This limit is now pushed to 10 nanometer regime. In fact, to be frank, this limit is pushed below 10 nanometer regime recently. So, that is how actually the technique has been so nicely developed, but we must give credit to Lis Meitner and Pierre Augier for discovering this technique, because this was a very fundamental technique which is used extensively in material science even till today. Before I actually talk about Auger spectroscopy in detail, let me just tell you, we know that any spectroscopic technique, whether it is electron spectroscopy or X-ray spectroscopy or Auger spectroscopy, it actually basically depends on the interaction of the radiation or the electron or X-ray or any other radiation with the material. And material means atoms, atom means nucleus and the electrons. So, when ions, electrons or photons, they are all actually source of radiation. This falls on the surface material, any atom actually, in the sense which is kept inside a vacuum. It can generate ions, electrons and photons. And if we analyze this which is generated because of this interaction process, we can get a lot of information about the atom. That is the basic principle of any spectroscopic technique, whether it is a electron energy loss spectroscopy or XPS or Auger. So, that means an interaction between the surfaces of a material with the incoming high energy radiation source generating other radiation like ions, electrons or photons is what is the basic thing of spectroscopy. Well, to talk about the Auger spectroscopy, we need to know a little bit about the electronic structure. As you know, electrons rotates around the nucleus in an atom. So, and these electrons have different energy levels, and all we know that the energy level depends on their quantum numbers, the principal quantum numbers, that is SPDF, then you have magnetic quantum number L, then you have the azimuthal quantum number, azimuthal quantum number L, magnetic quantum number M, and spin quantum number S. So, depending on the energy levels, we can actually split the electron energy levels in different cells, like this one is shown K, L, and M. K cell has 1s electrons, that is the inner cell or core electron cell. L cell has 2s or 2p electrons. M cell has 3s, 3p electrons. So the binding energy of electron will increase as you go closer and closer to the core level. So that means K level, K electrons will have more binding energies than M and so forth. And then you have basically at the above the occupied cells, you have what is known as Fermi level, and then you have vacuum. Now we can actually demarcate these energy levels in two ways. As you know, in the X-ray nomenclature, this one L basically K is K, so K is K, this 1s. L1 is known as 2s. L2p is known as L23. M1 is known as a 3, actually 3s corresponds to M23 correspond to 3p, and then you have 3d, 3e, 3, 4s and 4p levels and above. That is why actually X-ray people use the nomenclature, and this is atomic nomenclature. XPS we have used another kind of nomenclature. Now if I consider the electronic structure of a metal like sodium, what it has? Sodium has 2 electrons in 1s level, 2 electrons in the 2s level, then you have 6 electrons in 2p levels, correct. So that means K, L1, L2, 3, these are the energy levels created. So in a solid state, the core levels of atoms are little perturbed and essentially remain as a discrete localized levels that we know. And this the valence orbitals however overlap sometimes significantly with those of the neighboring atoms, genetic bands of spatially delocalized energy levels. So after knowing this, now let us talk about the physical basis of OGS spectroscopy. What is the physical basis of this particular technique? Well, I think I talked about XPS. Let me just bring in the XPS concept, and what happens in the XPS concept is we have X-ray source, which is high energy X-ray source. It is allowed to fall on a sample, and this high energy X-rays then basically interact with the electrons, core electrons of the atom, and eject the core electrons of the atoms, leaving behind a hole there. So then once it leaves behind a hole and the ejected electron goes out, and we have analyzed the ejected electron energy levels, kinetic energies, and that is how we actually do the analysis. So if I have to show it very nicely, I can just show it on the board. Let us suppose we have K level, this is K, this is L, and this is M. Right, and then you have EF, that is the Fermi level, and you have then vacuum, EVAC. That is how the energy diagram of a atom can be represented. Now if I have certain radiation like X-ray photon falls on these K level electrons, and what will happen? Because of these electrons, some amount of this electron, because of this X-ray photon, this electron at the K level will be ejected out, and then this passes through, because this is like very high kinetic energy. Normally the incident beam will have very high energy higher than almost 10 times higher than the binding energy of this electron in the K level. Because of this excess energy of the incident X-ray, the ejected electron will have a lot of kinetic energy, and because of this high kinetic energy, this electron will go out, and that is what we do measure in the XPS. So this is what is used in the XPS, as you know. I have discussed that. This is irradiative process, and this is also kind of leads to create a hole in the K level. Now let us discuss what happens in OGM. So, I draw the same thing here again. So, I have k level electrons, L cells, and then you have M cells, and then you have so k, L, M, and then you have right. So, now I have already created a hole in the k level electron because of this radiation. So, what will happen? This atom is now in an excited state because ionized, basically this is an ionized atom because one electron has gone out. So, because of that it has one because of this high energy state. So, what this atom can do to come to a lowest energy, some higher level electrons can jump. Suppose this level electron L1 here can jump into this hole or can jump to the k level hole and fill this space. And if it does so, what will happen? If it does so, this electron has jumped and filled the space. So, now what will happen? Because of this difference energies between the L and K, some amount of X-rays will be coming out, and these X-rays which will come out can eject out another electrons from the higher levels like M or L, M level or whatever, or maybe higher level, and this is what is called Auger electrons, and this is what is known as Auger process. So, that means basically what is done here is as follows, which can be seen from this picture very carefully. What I have drawn here and what I am showing in the slide is similar. So, because you have a hole created in the k level as the electron has gone out, so one electron from the L1 level will jump and fill the hole, and because of this there will be some energy released, and this energy can then eject out electron from suppose L23 cell, and this is what is known as Auger electrons. So, in a nutshell I can say ionized atom that remains after the removal of the core hole electron is of course a highly excited state, and will therefore will like to rapidly relax back to the lower energy state, and it can do by two routes. As you say, one is known as X-ray fluorescence route, other one is Auger emission route. Let us consider, because we are not talking about X-ray fluorescence here, that is a separate thing, we will consider only Auger. So, as you say here, this is what is the Auger source. So, therefore, a rough estimate of the kinetic energy of this Auger electron can be done by knowing the binding energies of the various levels. So, kinetic energy is basically Ek minus L1, that is what is the jump, minus L23. This was the difference which has created the energy, and then this is the binding energy of the electron, the L23 cell. So, therefore, basically Ek minus EL1 plus E23. The kinetic energy of Auger electron is independent of the mechanism of initial hole creation. This is very important. Initial hole creation can be anything. Basically, Auger process uses electron beams to create the hole, not the X-rays. So, basically it is very clear that the kinetic energy of this Auger electron is independent of whatever the process is used to create the hole in the inner shell or the core level core cells. So, normally in XPS, normally what is done is that in practice we use a very high energy incident beam, and the electrons like of the order of 5 to 10 kilo electron volts. So, holes will be produced by these electrons, or it can be produced by even backscatter electrons also. So, that how I hope now that these two processes, the difference between these two processes are clear to you. So, because of the creation of this Auger electrons is totally different from the XPS. So, energy of the Auger electron is also very small. Because it is very small, energy is much small as compared to the XPS electrons. So, the information which you can gather will be from very small depth of the surface of the material. So, to give you in much detailed perspectives, let us do it again. So, here the electron beam comes suppose this is the ground state of the electron, K level L1, L2, 3 and then above. Higher the electrons, it can be also photons, but normally we do not use any photons, we use electrons, and it rejects the electrons from the core level or K level, leaves behind a hole. This is what is ionized electron. So, one electrons then falls from the L1 level to fill this K1 level. Because of this, some energy released, and this energy then eject out L2, 3 level electrons, and the electron gets transported. This is what is in a nutshell whole Auger process. And this is what is shown here, Z plus H nu. This is Z is the atomic number of the material, suppose H omega is the energy of the electron, ZA plus electron level, and ZA plus electron level produces whenever Auger electron, it will be ZLBC plus electron A, that is what is the electron A, that is Auger electron. So, if you use a conservation law, EBA is energy of the material is basically N1 minus N of the two final state and the initial state, N1 is N is the number of electrons. EKA, that is the Auger ABC, ABC is the three processes, A is the beginning process, B actually intermediate process, and C minus U. U is basically the energy to remove the electron, this is there. So, Auger electron energy is independent of the excitation energy, as I have told you, U is known as the Auger parameter. Auger parameter is the machine dependent parameter. So, what are the nomenclatures? This is what is shown here in the whole process. Well, nomenclatures are very complex in a XPS. I need to discuss in detail about that. The XPS nomenclatures are basically like 2s, 2p half, 2p 3 by 2. You know, half is basically 1 minus half, and 3 by 2 is 1 plus half, and 1 stands for p. ASS, now the S basically stands for 0, and then if you use L, L will be corresponding to 2, so 2 minus half is 3 by 2, or 2 plus half is 5 by 2. This we have seen. So, what happens in Auger? As you see here, in this case, source comes, keeps a hole, this comes down, and the electron goes off. That is what is shown. So, in X-ray, in Auger we use X-ray nomenclature. So, what is this X-ray nomenclature? Conventionally used nomenclature is X-ray type in Auger. Suppose for example, K L1 L2 3, that is what is here happened, K L1 L2 3. This is a whole transition. When electronic levels are energetically well distinguishable, it is common to use most sub indices like L1 2 3, M2 3, M4 5. This also one can use. Very well distinguished atoms can be done that. For a group of transitions, sub indices are in many times omitted like KLL, KMM, MVV, or for transitions involving levels in the valence band, commonly used V instead LM and OP, for example M4 by 5 V. So, but normally we use this or this, other things are not extensively used. Let me just discuss in detail about a table and to show you so that you do not forget. So, basic nomenclature which is used in the SPS can be written like this. Suppose this is quantum number, this is quantum number, and this is suppose notation. So, we are going to notations both XPS and X-ray, and that is what is used in AES, right. So, quantum number means N, L and J, right. So, this is what we are going to do. So, let us suppose for quantum number N equal to 1, L equal to 0 and J equal to half. L is the azimuthal quantum number and J is the spin quantum number here. You can use, instead of J, let us use S, spin quantum number. So, and then we use basically what? We use 1s half. This is just 1s, there is no need of writing. In X-ray we use this as a K. So, if it is 2 quantum number, this becomes 0 and this becomes half. So, and what is this XPS we use? This we use 2s half, right. and this is corresponding in X-ray is L1. So, if you suppose 2 again quantum number 2 and 1.5 here. So, this will be 2s not 2p half basically, because 2l is 1, 2p half, and this will be L2 I guess, yes L2, and then if you use 2 1 1 3 by 2, 3 by 2 is 1 plus half 3 by 2, this will be 2p 3 by 2. This is what we have discussed, how 2p half and 2p 3 by 2 comes in XPS I have discussed, and this will be L3, right. Now, let us do something for 3 actually. When principal quantum number become 3, this is 0, this is half, this will be what? This will be 3s half, and this will be M1. So, if it's become 3 1 and half, so this will be 3p 5 by 2 half 3 half, so 3p half, and this will be M2. And last one, let me see, 3 1 3 by 2, 3 1 3 by 2 will be p 3 by 2, 3p 3 by 2, this will be M3, right, and so on. So, as you see here, K stands for 1s half, L1 stands for 2s half, L2 stands for 2p half, L3 stands for 2p 3 by 2, M1 stands for 3s half, M2 stands for 3p 2 by 2, and M3 stands for 3p 3 by 2. This 3 by 2 basically comes because of spin j pass L is suppose 1 here, so it becomes 1 plus half is 3 by 2. Okay, so that's how it comes. So basically in XPS we use these notations to demarcate different peaks. On the other hand, in OGR we use this notation. This is funny because these two techniques are same spectroscopic techniques actually, but we use different notations for this peaks, transitions. So that means if there is a transition form, suppose like this one K L1 L23, L23 is 2-3 levels, so it will be K L1 L23 or K LL, both are possible. If there is transition form K suppose L1 M1, then it will be K L1 M1 or K LM or K MM is also possible. Okay, all these things are possible, different kinds of combinations are possible. Well, to give you in a better perspective, so what is the difference between this photoelectron and OGS spectroscopy will be clear from here. Well, as you see here, 1s, 2s, 2p, this is energy level of an atom. At the different electron energy levels, basically then you have a Fermi level quantum band, quantum bands, and the vacuum and the free electrons. So you have an incident X-ray with energy k nu falls on it. It removes core level electrons. This core level electron goes out. So that means the kinetic energy of electron will be h nu minus binding energy of this electron minus phi. Specification is basically because of the machine. But in a OGM, what is happening? You have created a hole. Because of this hole, the electrons from the L23 jumps, and then emitted X-ray comes out. This X-ray is then generate or ejects out another electron from these L3 cells, and this electrons is known as OGM. So the kinetic energies obviously will be depending on K L1 and L23, and that's how we have calculated in the earlier also. Now next thing is to discuss is what is the OGS signal, or what is basically OGS, how does the OGS spectrum look like. In general, initial ionization is non-selective, because initial ionization means how the hole in the K level is created is non-selective, and initial hole may therefore be in various shells like K cell, L cell, M cell, any shells, because that depends on how the initial ionization has taken place. And then there will be many OGS transition possible for a given element. Some will be very weak, some will be strong. So RGS spectroscopy basically based upon the measurement of the kinetic energy of the emitted electrons of the RGR electrons. So each element in a sample being studied will give rise to characteristic spectrum peaks of various kinetic energies. So that is how RGS spectrum is basically will contain large number of peaks, and that creates many times a problem. To give an example, let us take the RGS spectrum of palladium metal. Palladium has a very large number of electrons in the outer cells or even inner cells, and this is generated by 2.5 keV electron beam to produce initial core electron vacancies, and hence to stimulate the RGR emission process. The main peaks of the palladium occurs between 220 to 340 electron volts. The peaks are situated between basically on a high background. That is why the problem in RGR. This mainly because of the secondary electrons are generated by multitude of inelastic scattering processes. So RGS spectra are often shown in differentiate form, that is why, and the reason for this is partially historical, partially because it is possible to actually measure the spectra directly in this form, and doing so get a better sensitivity of detection actually. The plot actually shows a S1 spectrum. This is the signal versus Ke. You can see here there is a high background because of the secondary electron, and these are the peaks which are coming out, which are between 220 and 340. But whenever we take a differentiate of this electric signal with respect to the energy level dN by d, we get a smoother background and the peaks can be seen very nicely. That is what is normally used in RGR. This one is not used in RGR. Well, to give you a much better idea, this is a plot between D and E versus DE with respect to electron, and this is basically from the silver. As you see here, this is Ne of silver, this is energy level electrons, this is the Ne for 10, and then this is dNe by E. Signals are much stronger when you plot dNe by dE versus energy levels. That is why we use all this. Now to give you some examples of these RGS transition lines. I have already discussed you different transitions. Let us do it for I think certain example. This is taken from a MSc thesis of University of Campinas long back. If you look at that, on this plot you have intensity versus kinetic energy of indium, element indium. You have both your XPS peaks which are here and RGR peaks which are here. RGS will have less energy than the XPS, less than 3400 or less than 3500 actually. EV is the energies of this RGR and higher than 3600 basically from 3s, 3p and 3d electron levels of the. This was done with the excitation with the titanium K alpha, which has energy of 4511 electron volts. So what do we see? We see all the transition like LMM, LMN transition. Indium has a large number of electrons, so therefore there will be large number of RGR transitions possible. So the ones which are basically very routine is L1, M45, M45. M45 is M45 from M45, and all others L2, M45, M45, again L3 also they are from L3 to M transitions, MM transition. Then this is actually called all LMN transitions. There are different element transition L1 to M45, N45, and then L1 to M45, M45, L3, L2, and so on. So basically these are all LMM transitions as you see here, and there are many, and there is only two. This is the one LMN, this is another one LMN, this is also LMM transitions. And these transitions actually can be detected very nicely in a XPS spectrum. Here although it is plotting dNe intensity or whatever energy coming out from the electrons, but many times if you plot dNe versus dE versus kinetic energy, dNe by dA is what is plot the slope of this curve basically, that will give you much better peaks. So for a given elements, several lines of RGR will be observed or seen. That is what is observed. So, Auger transition lines for different elements can be plotted like this. This is atomic number versus electron energy, and there are different elements starting from lithium to uranium, correct. So, what you see here basically KLL transition, KLMM transition, MMM transitions and so on. Red dots actually indicates the most intense lines which are seen in the spectrum. So, I could see here we can observe KLL transition till sulfur, as you can see here, because energy levels are small, the atomic numbers are small. So, therefore, as you go on we can observe seeing LMM transitions from atomic number about 12 to atomic number about 40, and then MMN transitions since at higher atomic number starting from 37 to about 84, 85, and then so on. You can observe actually and higher level transitions like these ones for very high atomic number elements. So, this is very important, because this table tells you what all transition you can expect when you are doing the Auger measurements. I think last one today's lecture I am going to show you is the analysis volume. As you know that when a certain energy source is falling on the sample material, it interacts with the material and it creates a volume of interaction, or interaction volume rather. So, the X-rays comes out from a large volume, then comes out these are actually Cartry X-rays as you see here, which higher than atomic number 4. A backscatter electron also comes out, secondary electron comes out from a Mars level. Auger electrons comes out only from 4 to 5, 50 Armstrong. This is the depth from which it can come out, very small. Depending on the spot size of the electron gun, it is possible to have spatial resolution, very small spatial resolution. In the direction perpendicular to the surface, the analysis volume depends on the electron mean free path. So, mean free path versus electron energy, if you plot, if you see a mean free path, basically first it decreases from gold to bottom to beryllium, then it increases till sodium. So, this is what is these two are the main factor. One is the beam size, other one is the mean free path. So, if you use a perpendicular measurement system here like that, then your mean free path becomes very important.